Hey y'all, we are Memphis Community University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we're going to be concluding our limit unit in the best way possible. We're going to be talking about derivatives. So you've probably heard of this word before, derivatives. They are a very important part about calculus. Along your calculus journey, you're probably going to be taking thousands of derivatives. So now it's time to introduce them. So what are derivatives? What we're going to see is that derivatives are really limits. They're special kind of limits, and they're the slope of what is called the tangent lines. So we're going to be introducing a lot of big notions today, so it should be a fairly exciting day, depending on our definition of excitement. But basically, we're going to be talking about limits, we're going to be talking about derivatives, and we're going to be talking about tangent lines. Once we do the introduction, we're just going to find the equation of the tangent lines, which will involve derivatives for a variety of functions. What we would recommend you do is watch our limits evaluating limits algebraically video, which is a few videos back in this playlist, so that you have a general idea of how to compute the limits once they come. But first, we do need to introduce limits sort of in a more theoretical way. Not limits, derivatives. Derivatives as limits. So this is the intro to derivatives. So intro to derivatives. So basically, we're going to start off with a nice little picture. A generic function f of x. So you might know, of course, how to find the slope of f of x through 2 points. It's just y2 minus y1 over x2 minus x1. But there was this guy named Isaac Newton, and he was not satisfied with this. He wanted to find the slope at exactly 1 point. So he wanted to find the slope at, for example, this point called A. So this is the point A, and this is f of A, is the y coordinate, and A. So he wanted to find the slope at this line right here. And this is what is called the tangent line. So again, this line is only touching the function at 1 point. So it seems like it's impossible to find the slope at this line because you usually need to find 2 points to find the slope of this line. Again, this is called the tangent line. This is the line we're going to be computing throughout this video. If you want to have a little bit of a Latin lesson, tangent comes from the word tango, tangere, tagi, tectus, I think. From Latin meaning to touch, meaning so it's just touching at 1 point. So what Newton discovered is that, well, you can only find the slope of the line really through 2 points. So he just has an arbitrary point like x and f of x. And what he does is he finds the slope between these 2 points. It's not exactly the same line, so notice that if I can dot this line, it's not the same line as the one he wants, but it's close enough. And he'll be able to get closer and closer and closer. So what is the slope of this line? Well, again, it's just y2 minus y1 over x2 minus x1. So if you have this point x, it's just f of x minus f of a, y2 minus y1 over x2 minus x1, x minus a. And what's going to happen is that notice that as this point gets closer and closer and closer and closer, so you have your point here, you draw a line between this point and a. You have the point here, you draw a line between this point and this first point. You keep going, and notice that if you get really close, you're eventually going to approximate the slope of this tangent line because the points will be so close together that they're at basically 1 point. And how does that work? Well, again, what we're going to do is we're going to let the x value get really close to a. And what is that notion that we've already talked about? That's what a limit is. So what is a derivative? A derivative is this limit. You're finding the slope of this between these 2 points until the points are basically the same point, and so that you're finding the slope of this tangent line where this point, you're finding the slope where this line is only touching at this 1 point because the 2 points basically became 1. And how do we write derivative? We're going to write it as f prime of a. So this means the derivative of the function at the point x is equal to a. Again, all it means is the slope of this tangent line at the point A. And how are we going to find it? We find normal slope, and we let the x and the a get to know each other very well, so that they're basically the same thing. So then we will have the slope of the tangent line. And this is the definition that we're going to talk about. Unfortunately, there's usually 2 limit definitions of derivatives that we need to introduce because they appear quite often. So the next one we're going to talk about is the limit as h goes to 0, h f of a plus h minus f of a. So this is what I call the h form of the definition of the derivative. I call this one the non-h form for obvious reasons. This one has an h, this one doesn't have an h. I'm not going to go as in depth with this one, but basically it's the same thing. You're starting off at the point A f of A, then you go to a point called A plus H. Basically you add an H. And again, you want these points to get really, really close together. So that's why you let the limit go all the way to 0. So as you get the limit, as you go to 0, you're going to eventually find the slope at this point where the line is touching only at that one point. So again, we're going to have two definitions of the derivative throughout this video. We're going to have the non-h1 and the h1, but they're both inherently sloped. So as you take these derivatives, even once you learn like things like the power rule and the quotient rule and the product rule and the chain rule, as you take 1,000 derivatives, what you always want to keep in the back of your mind is that derivatives are inherently sloped. It's the slope of a line. And what is that line called? The tangent line. And what's special about that line? It doesn't go through the function twice. It only touches the function at exactly one point. So you're finding the rate or the slope of a function only at that one point. So that's that. Today, what we want to do is we want to compute limits by finding, or compute derivatives by finding these two limits, and then the derivative will help us find the equation of the line, this line right here. So when we find the equation of the line, we're going to need two things, a point and a slope. The point will be pretty obvious. It'll be something comma something. It'll be given usually. And then the slope will be the derivative. So we're going to find that limit and then we're going to find that derivative and then we'll write the equation of the line. So let's see how this works. So I'm going to erase this. So now we're going for examples. So what's going to happen is we're going to have f of x being a function. Let's let our first function be something like x squared plus 3x. Then we're going to have a given a. So a is equal to, for example, 2. And then what's going to happen is that we're going to try to compute the derivative of this function, meaning the slope of this function at this point A. And then we're going to write the equation of the tangent line. So let's get started. So the first thing to do is try to find both coordinates of your point because it will be useful. So the point on this function is going to be 2 comma something, and what you're going to do is you're just going to plug in 2. So when you plug in 2, it looks like you're going to get 4 plus 6, so that's going to be 10. So this is going to be my point. Then I need a slope because I'm going to try to find the equation of the tangent line. We can write that as what we want. And again, the important thing about the tangent line is that it touches only at one point, so the slope is given by the derivative. So we do need to set up the derivative. So eventually what I want to do is find what is called f prime of 2. And ultimately you'll learn things like the power rule, the quotient rule, and the chain rule, but for now we only know limits, so we do have to set up a limit. I'm going to do this question in 2 different ways, one the non-h way and one the h way, so that you have sort of an idea of how to do both, and then we'll do examples with both later on. So first off, I'm going to do the h way, so remember, the non-h way, so remember that it's of this form right here. So we do have to form the limit in this case, but it's not going to be too bad. This is actually x goes to a in the general form. So what is a in this case? It's 2. So anytime I have an a, I'm going to plug in 2. So it's going to be the limit as x goes to 2, x minus 2. Then we have minus f of 2. F of 2 we calculated to be 10. So that's 10. And then finally, we write the function down. That's x squared plus 3x. So it's x squared plus 3x. So again, this is the non-h way. This is the general form. And in this case, it's this limit right here because x is going to 2. So the 2 goes in these 2 slots. The 2 also goes in here. F of 2, we found this coordinate for f of 2. That's why it's nice to find both coordinates. And we plug that into 2 again. We plug 2 into this function to find that second coordinate. It's 2 comma 10. So that's why we have minus 10. And finally, we just list the function out. That's f of x. So it's x squared plus 3x. So now it becomes old stuff. Hopefully, you again saw our evaluating limits algebraically video, which was a few videos in previous videos in our playlist. Sorry, I can't talk it all right now. I don't know why. But basically, we have this limit, and we're just going to try to compute this limit. So remember that in that video, what you want to do is you want to plug in a number and see if you get 0 over 0. But in this case, you do get 0 over 0. It'll be 4 plus 6 minus 10. That's 0. Over 2 minus 2, of course, that's 0. And remember that from that video, what you want to do is you just want to do something. Do the thing that's most natural. Follow your heart. So in this case, looks like we should just factor this guy right here, x squared plus 3x minus 10. So that's what I'm going to do. It's going to be x minus 2, I believe, times x plus 5 over x minus 2. We still have the limit, so we should rewrite limit as x goes to 2. And notice that we did something right because once we factored, good things happen. X minus 2's immediately cancel. So then all we have to do is plug in 2. Looks like when we plug in 2, we will get 2 plus 5 is equal to 7. So that was our first derivative. I know it was super exciting. Looks like f prime of 2, meaning the slope of the tangent line, is equal to 7. So finally, to write the equation of the line, you can write it in various forms. You have point slope form, you have standard form, you have y-intercept form. In my opinion, the easiest way, once you have a point and slope, it's just point slope form. It's just y minus your y coordinate equals slope times x minus your x coordinate. So in this case, it's going to be y minus my y coordinate, that's 10, equals slope, which is 7. That's given by the derivative, which was this limit. Finally, it's x minus the x coordinate, so it's x minus 2. And this is the answer. So a lot of work, but let me just try to recap it so that we sort of know the general steps. First off, you're going to be given a function and you're going to be given an a, an x coordinate. Keeping in mind that we want to find the equation of the tangent line of this function at a. So basically, we want to find the equation of the line that only touches the function at this number x is equal to a. So what we do is we first find the point. That's easy. Both coordinates, plug in 2 to find the y coordinate. Then what you do is you set up a limit because that's going to be the derivative. And it's a very special limit. It has to be the limit of the slope, basically. y2 minus y1 over x2 minus x1. There's two forms, the not h1 and the h1. We'll do the h1 immediately after this, but the not h1 is like this. And what you do is you just plug in all your givens where they're supposed to be. So there's 2 here, boom, boom. There's a function, that's this guy right here. And then finally, f of a is that y coordinate we found earlier. Then, once you write the limit down, you have to evaluate the limit, of course. You have to find what that limit is. But it's our general strategy on limits. Once you get 0 over 0, for example, you try to do something. In this case, it was factored. Once we factored, good things happened. We plugged in 2, 7. So that gave us our derivative. That gave us our slope of this line. Then what you do is you sort of write this line in point slope form. Y minus the y coordinate equals slope minus x minus the x coordinate, where the slope is the derivative. And that's how it works. So let's do the same question with the same point, but let's try to do it with the h way, just so we can get accustomed to both ways. So I'm going to erase this. And we're going to do the h way. So let me remind you what the h way is. So again, it's the same function, same point, same y coordinate as well, plugging in 2. And now we're going to try to do the h way. So the h way is written as limit as h goes to 0, h on the bottom, f of a plus h minus f of a. So it is a little bit of a trickier form, especially this f of a plus h part, but let me show you how it works. It works the same way as the previous one. What you want to do is you want to just start plugging in the givens where they go. So we have limit as h goes to 0, we're going to have h on the bottom. The thing that doesn't change will be the minus 10 on the end, because when you plug in 2, it will be f of 2, which we already computed to be 10. So at the very end, it is going to be minus 10. Then what you do is you find f of 2 plus h. So again, you plug in 2 anytime you see an a, not h, but a. So it's 2 plus h, and then you plug in 2 plus h into your function. So how do you plug something into your function? Basically, anytime you see an x, you're going to replace that with a plus h, which in this case is 2 plus h. So you're going to replace that with 2 plus h squared plus 3 times 2 plus h. So again, all of this was f of a plus h. Instead of having x's, I took my a plus h, which in this case is 2, so it's 2 plus h, into your function. And that's how it works. So this is my guy right here. And again, once you set up the limit, you just have to compute the limit. So let's see if we get 0 over 0, because we have to see that. You will get 0 over 0 basically. So when you plug in 0 into all these h's, again, you're going to get 4 plus 6 minus 10. So that's going to be 0 over 0. So now we have to do our limit strategies. It's no longer really a derivative question. It's really a limit question where we will need to find this limit. And the last question, we factored things because things look like they should have been factored. In this case, it looks like things should be expanded so that things will cancel. So let's see if that works. So we have the limit as h goes to 0. Then it looks like it's going to be 4 plus 2h plus h squared, because of this guy right here. Then it's going to be plus 6 plus 3h, I believe. Finally, we're not going to forget this minus 10 at the end. That was the minus f of a. Then we're still dividing by h, because always when you have the h form, it's divided by h. So now we have this limit right here. Let's see if we did it correctly. If we did it correctly, things should be canceling out. And notice that they do. Notice that we have 4 plus 6, which is 10, and I'll subtract off this 10. So now we're eliminated a few things because we did the algebra step correctly. Finally, it looks like there's going to be more cancellation that's needed to be done. Notice that all the remaining terms all have h's, so we can divide by h from every single term, and we won't be butchering fractions because they all have an h in common. So we're going to divide by this by h, this by h, this by h. Obviously, when you divide h squared by h, you're just going to have h left. So it looks like we're going to be left with the limit as h goes to 0. Then it's going to be 2 plus 3. Sorry, I didn't factor things correctly. I was doing it too quickly, but 2 plus h times 2 plus h is 4 plus 4h. My apologies there. That makes more sense. It's going to be 4 plus 3. 4 plus h plus 3. And then when you plug this in, you will get 7 again. So again, let me try to sort of atone for my mistake there. 2 plus h squared, that's 4 plus 4h plus h squared. It should be 4 plus 4h plus h squared because it's 4 plus 2h plus 2h plus h squared when you expand 2 plus h times 2 plus h. But still, once we did that, everything sort of simplified. We first carried out the 4 and the 6, we added those together, that subtracted off the 10, and finally, even if I had it incorrect, all those terms did have h's, so we eliminated those h's, h, 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 h. So we were left with 4 plus h plus this little 3, and notice that when we let h be 0, it will be 7. So that's the answer. That's the derivative. And let's write the equation of the line. Of course, it's the same thing because we got the same answer because we have the same equation and the same point. But again, how I like to do it is point slope form. Y minus the y coordinate, which is y minus 10, equals slope times x minus the x coordinate. And this is the answer. So again, even with the h form, it's still the same thing. You first find your point, then you take the derivative. To take the derivative, you need to set up your limit. In this case, we chose the h way. It's pretty arbitrary which way you're going to do. You can do either one and of course get the right answer, just like we did in the previous one. We both got 7. When you have this set up to the limit, you just have to evaluate that limit. In this case, the best way was to expand this limit. This was a little bit weird and I was being kind of careless, but when you expand this, it should be 4 plus 4h plus h squared. Then you distribute this 3, so it's 6 plus 3h. It was good once we sort of checked our work, once I recognized my mistake, because everything canceled out. The 6 and the 4 canceled out with the 10. The h's all canceled out, and we were left with 4 plus h plus 3. That's 7 when you let h be 0, and we got the same answer. So again, it's the same thing. Set up the limit, do the limit by doing something algebraically, and that will be your slope and derivative. So let's practice 2 more questions, one with the square root and one with some fractions. So let me erase this. So again, we're still going to try to find the equation of the tangent line, but we're going to change the point and we're going to change the function. So in this case, I'm going to do something like 2 over x. And then my a is going to be, let's say, 5. And for this one, let's choose the non-h way to form it. First off, you do need to find the point. So we can write the word point down. Again, all you do is you take your x coordinate, which is 5, and you plug it into your function to find the y coordinate. Looks like we're going to have 5 over 2/5. So then we need to find the derivative. The derivative will be notated by f prime of 5, and we're just going to form the limit. Because we're doing this for the first or second time, I'll write the general form again. It's the limit as x goes to a, where in this case a is 5, f of x minus f of a over x minus a. So this is the form. So let's try to write it for this specific example. Notice that when you plug in 5, it'll be the limit as x goes to 5, x minus 5, because a is 5, I replace all of those. The function is 2 over x. And finally, the a is 2/5. So this is going to be our guy. Now we don't have to think about derivatives anymore. We just have to compute this limit right here. So if you want, pause the video, of course, if you want to practice with limits or fractions. Think about how we did it in our previous videos. when we had fractions. I'll give you 1 second, I won't watch your work. Let's just get started. So first off, you recognize that it's 0 over 0 because you let x be 5 and you'll get 0 over 0, 2/5 minus 2/5. So now we're doing the limit. If you remember, to do limits with fractions, what you want to do is you want to combine the fractions. So it looks like we're going to have the limit as x goes to 5. The best way to combine these fractions is with the common denominator, and the common denominator is going to be 5x. So it's going to be 5 times 2 over x minus x times 2 over 5. And there's going to be 5 right here, and there's going to be x right here. So again, for this fraction right here, I multiplied everything by 5 over 5. And for this fraction right here, I multiplied everything by x over x to get this common denominator. Keeping in mind that we still have x minus 5 on the bottom. So x minus 5. So then, let's try to actually combine the fraction because that was the point of this. The limit as x goes to 5, then it's going to be 5x, x minus 5. And then finally, why are we doing this? It's so that we can get 2 times 5 minus x. So notice that when we have 10, this would be 5 times 2. 10 minus 2x, that's the same thing as 2 times 5 minus x. So remember that when you're doing these questions, once you do the algebraic step, which was this step right here, good things should cancel out. So keep in mind that it's a little bit harder to see how this cancels. You have x minus 5 and you have 5 minus x. But keep in mind if you have something minus something, a first thing minus the second thing, that's the same thing as negative the second thing minus the first thing. So 5 minus x is the same thing as negative x minus 5. So we can rewrite this as the limit x goes to 5. That's the same thing as 2 times the negative. So 5 minus x is the same thing as negative x minus 5. So I'm going to write it like that. Over 5x over x minus 5. If you don't know fractions, well, these things do cancel out. Because when you're dividing by this fraction, it's the same thing as multiplying by 1 over x minus 5. So these things cancel. When you plug in 5, you'll get an answer. It's going to be negative 2 over 5 times 5. That's negative 2 over 25. So now we're ready for the answer. Point slope form. Y minus the y coordinate, y minus 2/5 equals the slope, which is given by the derivative, which was this limit, negative 2 over 25, x minus the x coordinate, in this case 5. So that's this limit. Again, the same thing as the previous examples. You set up the limit however you want, either the h way or the not h way. We'll practice the not h way or an h way in the next example because we did a not h way in this one. But once you practice this limit and set up the limit, you have to do the limit. In this case, how do you do limits involving fractions? You combine the fractions using common denominator. Just be careful that 5 minus x over x minus 5, that cancels out to be negative 1. So we're left with negative 2 over 5x. You plug in the number at the very end, 5 times 5, that's 25. That will be your slope, negative 2 over 25. That's the slope of the tangent line. That's the slope where the line is only touching at this one point, and somehow through the magic of limits and calculus, we're able to find the slope of that line even if we don't have 2 points, we only have 1 point. So that's really the point of this. I didn't mean to say the word point that many times, but it's y minus the y coordinate equals slope minus x minus the x coordinate. So let's do one more. Let's do a square root example. So let me erase this. So we're going to just do something fairly simple. Let's do the square root of x plus 2. And we're going to do we need a nice square root, perfect square, so we're going to do a is equal to 16. So for this one, why don't you try to practice setting this up? Why don't you try doing the h way, and then why don't you try to compute that limit using limit methods that we learned in the previous video. I'll give you a second. If you don't want to do it, just hold on for 4, 3, 2, 1. Let's try to do this together. So first off, again, normally what you want to do is you want to find the point. So in this case, when you plug in 16, it'll be this 16 comma, well, the square root of 16, of course, is 4. So it'll be 4 plus 2, which is 6. So that's going to be our point. And now we have to set up the derivative. So the derivative is going to be f prime of 16. And the general form of the h way is the limit as h goes to 0, h on the bottom, f of a plus h minus f of a. So here we're going to try to set this up in this specific example. It's going to be the limit as h goes to 0, h on the bottom, And then what's f of a? Well, f of a is that point that we found earlier, the second coordinate. The y coordinate is going to be -6, so there's going to be a -6 at the end of this. And then a plus h, remember, you'll take your a, which in this case is 16, so it's going to be 16 plus h, and you plug it into your function. So it's going to be the square root of 16 plus h. There is a plus 2 here, so this is going to be my function here. Before we start evaluating this limit, I'm going to do a nice easy step. I'm going to do 2 minus 6 just to make our question a little bit easier. So it's going to be the limit. Maybe I need to go to the next line. The limit as h goes to 0 over square root of 16 plus h minus 4 over h. So that's going to be my limit there. Keeping in mind that we do have 0 over 0, because notice when you plug in 0 here, you'll get square root of 16, that's 4. 4 plus 2 is 6. 6 minus 6 is 0. So now what we have to do is our do something set, no longer a new thing, really a review from that evaluating limits video. Remember that if you have square roots, the thing to do is multiply by the conjugate. Keep in mind that the conjugate is based off this negative and not based off this plus. So what we're going to multiply by is the square root of 16 plus h minus plus 4. So again, the conjugate is just writing, instead of minus 4, it's plus 4. And why are we doing this? It's because when we multiply these numerators together, sorry, I can't speak. But when we multiply by these, man, I really can't speak. When we multiply these numerators together, we'll get rid of the square roots. I do not know I had so much trouble with that, so let's move on. Of course, you can't just arbitrarily multiply by things you want. You need to only multiply by 1 so that your quantity remains consistent. So we're going to multiply by the conjugate over the conjugate. So it's going to be 16 plus h plus 4. So let's see what happens here. Well, square root of 16 plus h times square root of 16 plus h. Again, we're doing that so we can get rid of the square roots. So that's going to just be 16 plus h. Finally, it'll be minus 4 square root of 16 plus h plus 4 square root of 16 plus h. They're going to cancel out because we have difference of squares on the top. So it's going to just be minus 16 over h times square root of 16 plus h plus 4. So we have this guy right here, and then notice that it looks like we're doing correct things because these 16s immediately cancel. So we'll be left with only h on the top, and we have h on the top, we have h on the bottom. Those cancel out. Just a little bit of a cancel fest, but we definitely don't mind because it's making everything easier. Finally, you plug in 0, and that will be the limit. So it's the limit as h goes to 0 of this quantity right here, 1 over the square root of 16 plus h plus 4. When you plug in 0, you'll get square root of 16, which is 4. So it looks like in the denominator, we'll get our final answer of 1/8. So that's the answer. Again, the same setup as before. In this case, we chose the h way. When we chose the h way, we did this limit. We got 0 over 0, so we had to do something. In this case, it was multiplied by conjugates. We multiplied by conjugates so that things cancel out beautifully in the numerator. And then finally, we plugged in 0 because that's the number that h is going towards. And we got 1/8. So the final answer is going to be y minus the y coordinate. Y minus 6 equals the slope times x minus the x coordinate. 1/8 times x minus 16. And that's our answer. So that was our last find the derivative at a number. But the derivative, as you'll see, can also be seen as a function. So instead of finding the derivative being only at a point, meaning the slope of the tangent line or the slope of the line touching the function only at that one point, what we can do is we can come up with a function so that when we plug in a number into the function, we will be able to find the slope at any number we want. So that's going to be our goal here. Not only thinking of the derivative at a certain number, but we're going to try to think of the derivative at every single number, whatever number we choose to plug in. So what we're going to do for our last question is we're going to find the derivative of a function at any single x. And in order to do that, what we need to do is we need to do the h way. So let's try to see how that works. So again, we're trying to find the derivative at a function so that once we have that function, we'll be able to find the slope of the function at any single point we want as long as we just plug it in. So in this case, we're going to let a be x because we don't know what our a is. We're not finding the equation of the tangent line. All we're doing is we're trying to find f prime of x. And then finally, we're going to have a new function here. Let's try to keep it somewhat simpler. Let's do x squared minus 2x plus 1. So again, what I want to do is I want to find not just f prime of 3, the slope at 3, or f prime of 4, the slope at 4. I want to find f prime of x, the slope at any single x that I want. And again, because you have this x and a business that they're the same, you can't do the non-h way, you have to do the h way, which is why the h way is introduced. It's the limit as h goes to 0, a plus h with a function minus f of a over h. So let's see how this works. So this is going to be a little bit nasty, but sometimes our work gets a little bit nasty, but it's the same thing as normal, except that instead of x's or a's, we have x's. So in the bottom here, we have h. This is the generic form. So let's plug in let's find what this is in this specific case. So when we plug in x, it looks like it's going to be x plus h, and we're going to plug it into the function. So instead of having x's, we're going to have x plus h instead. So it'll be x plus h squared minus 2 times x plus h plus 1. And I'll put this in brackets. So again, the quantity in brackets that I have written here is just f of a plus h, where a is x. We took our function, we took x plus h, and we shoved it in wherever we saw an x. So it's x plus h squared minus 2 times x plus h plus 1. Finally, we do have to subtract off f of a. Unlike our previous examples, f of a isn't a single number because we didn't plug in a number. F of a is just f of x, so we're just going to subtract off this. It's going to be x squared minus 2x plus 1. So now we have to do this limit. The limit, again, will have x's in the answer because we're going to be able to plug in any x we want. Looks like how are we going to try to compute this limit? Well, the best way is just to expand everything and hope that things cancel. Hopefully, I can expand things better than the first time. So it's going to be equal to limit as h goes to 0. We'll write a nice long fraction bar, h, and we're going to explain all of this. So it looks like it's going to be x squared plus 2xh plus h squared. When you can FOIL out x plus h. Then, because this negative 2 is multiplying each of these terms, it's going to be negative 2 minus 2h. And finally, there's a plus 1 at the end. That is the simplification of only the quantity in the brackets. So we still have this minus action, but notice that this negative should distribute to every single one of these terms. So it's going to be minus x squared plus 2x minus 1. So we have this long fraction, and notice that things will cancel out once we expanded all of this. It's the same general strategy as normal. We get 0 over 0. If you plug in 0, you'll get exactly this. So it'll be 0 over 0. So you do what your heart tells you to do. In this case, it was expand this crazy monster. But notice that the expansion of this crazy monster, I can't even talk anymore at all. But the expanding of this long guy right here brings good results because things immediately cancel. So let's see what cancels. Looks like this 2x and this minus 2x will cancel. Looks like this 1 and this minus 1 will cancel. And looks like this x squared and this minus x squared is going to cancel. So now we only have these 3 terms right here. 1, 2, 3. So let's write them down. So the limit as h goes to 0 over h, 2xh plus h squared minus 2h. Again, of course, we can keep more canceling out h's because, again, every single thing has an h, so we're allowed to cancel things out. This h will cancel, this h will cancel, this h will cancel. Finally, h squared divided by h is h. So we have the limit as h goes to 0 of 2x plus h minus 2. Finally, we'll let the limit as x goes to 0. We plug in 0 for h, so we're left with the final answer of 2x minus 2 because as h goes to 0, we plug in 0 for h, so this goes away and we're left with 2x minus 2. And that's the answer. F prime of x in this case is 2x minus 2. So what is the significance of this guy right here? Well, basically, if you drew out this parabola, x squared minus 2x plus 1, and you wanted to find the slope only at the point 3, you would just plug in 3 into this function. This is the derivative. The derivative gives you the slope of the tangent line, the specific point, what you want. So when you plug in 3, you'll get 6 minus 2, which is 4. So that means that the slope of this function only at the point, I don't even remember what I said, 3 is equal to 4. And you can plug in any number you want. You can plug in 5 and find the slope only at 5. You can plug in 7 and find the slope only at 7. So that's the magic of derivatives. You can find slopes only at 1 point as opposed to 2 points from our algebra days. So hopefully this video has been useful for you. We introduced derivatives sort of in a theoretical way. We saw that there was 2 definitions of the derivative in terms of limits. And what we did for the majority of this video is found the equation of the tangent line for various functions at the points. And how we did that is we set up these limits. We recognized that derivatives are limits themselves. So we had the h way and the not h way. Once we formed those limits, we used our algebra skills to evaluate those limits. But of course, this process is quite lengthy. So if you want, I'm going to be linking the Girls Teach Calculus video of this video of Introduction to Derivatives to the description of this video, where one of my former students practices a host of these questions where she finds the equation of tangent lines of various functions at various points. Some of them will involve fractions, of course. Some of them will be polynomials like this, where she might be expanding, she might be factoring, things like that. Some of them will involve square roots and fractions. And then finally, she does a few questions at the end, I believe, where she's finding f prime of x of generic functions and not just at specific points, just like this last one right here. Keep in mind that this is derivatives, and again, you're going to be taking derivatives a lot throughout your calculus career. You're probably not going to be computing derivatives in this way, so this does conclude our limit video. But if you want to watch our next playlist, perhaps an even more important playlist, I will teach you how to compute all these derivatives that might appear on the AP exam, for example. So we're going to be doing power rule, we're going to be doing product rule, quotient rule, and chain rule, of course. And what we're going to be able to do is go from here to here really in 1 second. What's the derivative of this? It's 2x minus 2 because of the power rule, and we don't have to do any of this long work. So be on the lookout for that. Hopefully I'll see you then during that playlist. But thanks again for watching this video. If it was useful for you, give us a like and subscribe because it's always useful for us. Hopefully I'll see you soon in that derivative playlist. But no matter what, thanks again for watching, just like normal.